Okay, let's begin. First question. I've represented a function f here, and I'm asking for the following things. So, first of all, f of -1. Okay, so this shouldn't be too hard. F of -1 is f when I input a -1. So when I input a -1, I get a 3. Okay, so this should be a 3. Nice. Inverse of f when I input a -1. Okay, everything is gonna be switched now. So we have different ways of doing this. We can either, let's write down the 3 again. We could either draw the inverse of f, right? We could draw the reflection and then do this exercise. We could as well do a table of values. I'm gonna actually do that. We could do a table of values and then see, okay, so for f, when I input a -6, I get a -4. When I input a -3, I get a -1. When I input a -1, I get a 3. And when I input a 5, I get a 5. Those are my key points. So the table of values for the inverse is going to be x, and fx -1 is going to be the opposite. So -4, -6, -1, -3, 3, -1, 5, 5. So here, with this table, I'm going to check what is the inverse of f when I input a -1. Oh, I get a -3. So this should be -3. Don't think it's because we've switched the sign, eh? That's just a coincidence. Another way of doing it, without even doing the table of values, would be saying, okay, so for the inverse of f, the outputs are going to be the inputs now. So I got to check for -1, which output I get. I mean, for the output, -1, which is going to be the input now, which input, which is going to be the output now I get. Anyway, instead of looking at the horizontal axis and then vertical, you look at horizontal and then vertical. Maybe it's easier like that. Yeah, so -1, and then I get a -3, which is the answer we got here. Nice. And what is the inverse of f when I put a -1? Okay, so I've got the table of values for the inverse of f. If I want to invert it again, I can do the same thing, right? So the inverse, sorry, let me do it properly. The inverse of x is going to be, again, switching everything. So I'll end up getting -6, -4, -3, -1, -1, 3, 5, 5. And what is this? This is nothing else than just f, right? They match. Therefore, when you have a certain function, right, and you do the inverse of the inverse, you end up just having the function again, because it's like you went back and forth again. Anyway, so this would be a 3 again, right? When you put a -1, you get a 3. Okay, next one. Exercise. So they're giving me a function f and they're asking me to find the inverse. Let's go. So I'll write f equals x3 -4. I'm getting rid of the brackets because I don't like it. You can leave it if you want to. My goal is to isolate the variable, so I'm going to pass the 4 into the other side. And then the power of 3 becomes a cubic root. Before doing this whole process, you should really check if it has an inverse. I know that it has one because this is a polynomial and this term has an odd degree, so no problem. And this is actually my inverse function. Now I switch the names of the variables and I end up getting x plus 4 equals f x inverted. So that would be the first question. This is the inverse of f. Nice, not really hard. Now they're asking me the x-intercept of the inverse. Now there's two ways of doing it. We know that the x-intercept happens when the function is equal to 0. So cubic root of x plus 4 should be equal to 0. The cubic root goes onto the other side as a power of 3. 0 to the power of 3 is 0. So x plus 4 equals 0. So x equals minus 4. That's the x-intercept. Another way of doing it, it would be, if the x-intercept is hard, which in this case it wasn't really hard, you could say, okay, so the x-intercept of the inverse is the y-intercept of its inverse, or the original function. So I could just literally do f of 0, which is easier, and then 0 to the power of 3 minus 4, that is minus 4, which is even faster. Usually determining the y-intercept is easier than the x-intercept, and that's one reason why inverse functions can be really helpful. Sometimes it's really hard to find the range of a function. You find its inverse, and then it's easier to find the domain of the inverse, and the properties are switched, so there you go. Alright, let's do the next exercise. If n is a parameter and belongs to the naturals, this is what this means. If n belongs to the naturals, remember natural numbers are 1, 2, 3, 4, 5, so positive integers. Justify which functions are strictly non-invertible. We got to remember that a non-invertible function happens when a polynomial has a term with an even degree, right? So, I mean a term with a variable. If n, we have to imagine that n can be any natural number. Is this always going to be even? Well, it can be even, because if n is equal to 1, I'll get 1 plus 1, which is 2, and it's even. But if n is equal to 2, I'll get 2 plus 1, which is 3, which is odd. So it depends. For certain values of n, it is not invertible, and for certain values of n, it is invertible. So it is not strictly not invertible, right? They're saying no matter what value of n you put in, it does not have an inverse. Well, I can't guarantee that. So this one is not strictly non-invertible. Alright, next one. So in this one, I'm gonna first try to simplify this. N plus 1 plus n plus 1 ends up being 2n plus 2. Okay, so what is any number times 2? Any number times 2 will always be even. That's the definition of an even number. If I put 1 times 2, 2. If I put a 2 times 2, 4. A 3, 2 times 3, 6. I'll always get an even. And what happens if I add 2 to an even number? If I do even number plus 2, I'll always get an even number, right? For example, 6 plus 2, 8, 10 plus 2, 12. Therefore, this will always be even for all values of n. This means all values of n. So this one is strictly non-invertible. Alright, so I'm going to highlight it. It's strictly non-invertible. Let's go into the next one. 3n plus 1. So what happens when I multiply a number by 3? When I multiply a number by 3, sometimes I get odds. For example, 3 times 3 is 9. But sometimes I get evens. For example, 3 times 4 is 12. So sometimes I get odds, sometimes I get even. And then I'm adding 1. What happens when I add, for example, 9 plus 1? I get an even. But if I do that to an even number, 12 plus 1, I get an odd. So it's not going to be strictly non-invertible. Depends on the value of n that I put in. Actually, if you want the full answer, if I input odd numbers like 3, it's not invertible, and if n is an even, it is invertible. Weird, right? Okay, so last one. 2n plus 1. So we already said that 2n is always even, And if I add 1 to an even number, I'll always get an odd number. For example, 2 plus 1 is 3. So this one is strictly invertible. No matter which value of n I put in, it will always have an inverse. So the only function that was strictly non-invertible was this one. Okay, next exercise. Find f for the following equation where the inverse of x plus x minus 4 all of it squared equals x squared. So the first thing I'm going to do is I'm going to start by developing this binomial, and I'll get x2. 4 times 2 is 8, so 8x. 4 squared is 16. So that should equal x squared. Now I'm going to bring this whole expression onto the other side. Everyone will get its sign changed. So I have this x squared right here, and then minus x squared plus 8x minus 16. Nice. I'm very happy because these two cancel. And then I end up having that the inverse of f is 8x minus 16. Right, but I'm not looking for the inverse of f. I'm looking for f. So who's the inverse of the inverse of f? That's f, right? Remember we said that? So I'm going to find the inverse of this function to go back to f. Okay, so again, I want to isolate x, so f is equal to 8x minus 16. Let's isolate x, 16 onto the other side, adding, and now the 8 goes dividing, and I'm actually done. That's it. That's the function I was looking for. This function, I'm gonna write it properly, is x plus 16 divided by 8 equals fx, which has an inverse 8x minus 16, which completes this condition that they were asking me. Okay, this is everything for this video. Hope it was helpful.